Okay, so welcome along, ladies and gentlemen, to your weekly SETI seminar. Today we're very lucky to be joined by Tony Zee, who's come up to us from UC Santa Barbara, where he's at the Kavli Institute for Theoretical Physics. Tony was brought up and educated in Sao Paulo, Brazil by American Felician nuns, and then he did his bachelor's at Princeton, and then did a PhD at Harvard in theoretical physics. His advisor was Sidney Coleman. Then he went to the Princeton Institute for Advanced Studies for his postdoc, and he was also at that time an Alfred P. Sloan Fellow. Then with short stays at University of Pennsylvania and University of Washington, he made his way back to the California and UC Santa Barbara, where he's been since 1983. Tony is the author of several books, including Quantum Field Theory in a Nutshell and Einstein Gravity in a Nutshell, which just came out last year, and also books for general audiences, including Fearful Symmetry with Roger Penrose, and a book on Chinese food, Swallowing Clouds. His career interests have focused around high-energy physics, field theory, cosmology, biophysics, and condensed matter, mathematical physics as well. So today he's going to talk to us about a topic very close to SETI and the SETI Institute, looking at how future civilizations, or how more advanced civilizations, might communicate between the stars. So please join me in welcoming Tony.
Thank you very much. I'm very pleased to be here. I've heard about the SETI Institute for quite a while. It's great to have this opportunity to come up here. I especially like to thank Adrian Brown for inviting me. Okay, so today I'm going to talk to you about galactic communication between technologically advanced civilization. So, the first thing I'm going to say is that, first of all, this is not my usual audience. I'm a theoretical physicist and primarily a quantum field theorist and not a professional SETI person. So, there are a lot of SETI details that I'm not able to, and I'm not willing to, I'm not capable of going into details. I also cannot quite gauge the audience. I was told that maybe a significant portion of the audience consists of the general public. So that's great. I welcome questions from the general public at the end. And this field is wide open, and there are, as far as I know, since I'm not an expert myself, that there are no real experts in this field. So my involvement with SETI consists mainly of 3 papers, and each less far out than the preceding by my estimation. So I started out writing a really far out paper, and then I became more and more conservative as the time went on. So maybe that means that I'm moving in the right direction. So the first paper I wrote is called Message in the Sky with Steve Hsu, and was published in 2006. So this is a pretty far out paper in which we claim that there might be a message embedded in the cosmic microwave background. And I still think that this is a very interesting idea. But Steve might have been driven out of academia by this paper. Well, he's not out of academia, but he's out of being a real person in academia, becoming a very high-level administrator. And he told me that when he gave up his professorship and became vice president at Michigan State, his salary went up by a factor of 3. So the second paper I wrote on this field is with John Leonard and Sandeep Bhagwasa, called Galactic Neutrino Communication. And the third paper is called the Cepheid Galactic Internet, with the same 2 friends of mine, plus Ralph Kudrytsky. And they're all based in Hawaii. And so in this collaboration, there are two high-energy theorists, one high-energy neutrino experimentalist and one astrophysicist. So today I'm actually invited to talk about the Cepheid galactic internet, but I'm going to start with the galactic neutrino communication. Is there a pointer? Oh, the mouse. Oh, okay. Oh, okay. Okay. Because I just been playing with my iPad for too long. I'm tempted to go like this. Okay. So I'm actually going to start talking about the galactic neutrino communication and the Cepheid galactic internet. So the search for extraterrestrial intelligence has gone on for several decades. And I think for this audience, I mean, again, I have trouble judging the audiences. So I'm using the same transparencies. I inherited some of these transparencies from my collaborator. And also these are the same transparencies I used at UCLA, which consisting of a different audience of more theoretical physicists. So, but I think everyone here probably knows that the search has gone on for many years, and many decades in fact, and it's focused within radio or optical bands. But in contrast to electromagnetic waves, for photons, of course obscured and by the interstellar medium, which is largely opaque to photons, but neutrinos, in contrast, arrive almost without attenuation. The second point is neutrinos are very rare, and from a given direction, all but totally negligible, especially at high energies. There's no known physical process that will produce high energy neutrinos, and I'll specify what I mean by high energies. So there's almost the signal to noise ratio would be extremely good. The other thing is that even when photons are not completely blocked, there's scattering, which introduce jitter in arrival time as well as direction. So on the other hand, neutrinos you can encode for by using just time interval between the quanta of arrival. So furthermore, you could also encode, as I will explain, encode information using neutrinos versus anti-neutrinos. Photons, of course, is its own antiparticle. There's no distinction. Okay, so again, for a general audience, very quick reminder of neutrinos. So if we want to communicate neutrino communication, we might ask this guy what energies are best. And in fact, this guy in our civilization figured it out. And he figured it out that he proposes the theory of neutrino scattering. And when a neutrino scatter on matter, the cross-section rises linearly with energy until about 100 TeV. 100 TeV is, of course, TeV is, of course, 1,000 GeV. So this is higher than LHC that you read about in the newspaper. And then after that, it rises logarithmically. So the cross-section actually rises very fast with energy. In fact, the signal to noise per neutrino goes up something like the 6th power of the energy. So I already said that low energy neutrinos are typical of nuclear, stellar, and supernova. So when we talk about very energetic, very energetic astrophysical processes such as supernovae, we typically think of very high energy particles being emitted, but those are, by the standard particle physics, is actually very low energy. So as I said, the signal to noise ratio would be, if we use low energy neutrinos, signal to noise ratio would be large and the cross section would be very small. So any advanced civilization probably use high energies. So we are, of course, not the first to propose using neutrinos for interstellar communication. There's an earlier paper by Pasikoff and Kuttner, and then there's a paper by Leonard, Pagvasa, Simmons, and Tata, and then also a paper by Selagazzi in 2008 after our paper. So in fact, how I got onto doing this paper was that after writing that paper with Steve Hsu, he was really, by the way, he's also a very wealthy Silicon Valley entrepreneur. He was interested in going to administration. So I tried to interest him in neutrino communication, but he was not that interested. And so I happened to meet Pakvasa at a dinner in Taiwan, of all places, and at a physics conference in Taiwan. And so this is how this collaboration started. And it turned out that Learned et al. In 1994 wrote a paper. In this paper that I mentioned, they talked about producing Z0 at rest. The Z0 is, of course, one of the, as you know, W and Z are the two primary basic gauge bosons of the weak interaction. And so neutrinos will be produced at very high, at 45 GeV, at half the mass of mz. And there's no known natural source for that. But the neutrinos will be emitted in spherically symmetric distribution, and antineutrinos would also be produced. So that's not so good. Okay, so we try to improve on this. So in this talk and in this work, we're not going to speculate on the motivation for communication, but rather focus on the physics issues. So presumably, when an advanced civilization wants to communicate with a civilization like ours, which we might call a technologically evolving civilization, there are presumably two stages. The first stage will be just to get our attention, to say that, hey guys, we are out here, and then to send information, for example, whether or not string theory is the way to go. So don't waste your time on that or something. So it would save a lot. Anyway, so there'd be very large time scale involved. So it presumably be monologue for a while. But all these considerations applies, of course, to both photons and neutrinos. There are many possibilities of why the ETs would be communicating. For example, a ETI might be sending information to military outposts by focused beams, and we happen to be in the way. So, for example, they were sending a neutrino beam to their military outpost, and the Earth happens to be in between. The probability of this is presumably very, very small, geometrically. So this probably can be neglected. Now, there's, I think, an important paper by Rose and Wright, 2004. Since I'm new to this field in SETI, I don't know any of these people. I've never met Rose and Wright, so maybe they're here in the audience for all I know. Are they? Oh, okay. So they wrote what I consider, they made a very interesting point, what I consider to be an interesting point, which is that transmission of a large amount of data by both photons and neutrinos is highly inefficient. And so if you want to transmit a large amount of information, it's better to leave an artifact and then send the information on how to find the artifact. Okay, so that's an interesting point. So, but then we question in this paper that Steve Xu and I wrote, why people assume that there has to be a large amount of data, okay? So for example, what would the message be? So in our paper, one of our suggestions was that, for example, we could send a Cartan matrix for gauge algebras, which gauge algebras we're talking about, underlying the electroweak and the strong interaction. Our civilization, as you know, has advanced to the point in which we have unified electromagnetism with weak interaction. We also know the theory for strong interaction, and we know how these three interactions are unified. And we know the gauge group for all of them. So we can write down the Cartan matrix for them. The Cartan matrix is very, very compact. It consists of three numbers, 2, -1, and 0. So now, we don't know how gravity is combined with these. So why would anybody, advanced civilization, want to tell us? Well, it's very clear. If you know any theoretical physicists at all, you know they have almost an irresistible urge to publish right away. Every time they have a thought and an idea they want to publish. So any advanced civilization presumably would have the same urge and say, you dummies out there, we know already what the 3 of the 4 fundamental interactions consist of. Okay. Now, so one of the advantages of sending out a focused beam of neutrinos rather than broadcasting in the electromagnetic wave is the advantage of not being seen by everybody. So maybe there's danger of attracting unwanted attention, right? So perhaps an advanced civilization would only want to transmit to a technologically emergent society, a TES such as ours, so who cannot threaten them. So perhaps they've become aware that we as a TES are constructing or have constructed large neutrino detectors. And these are huge detectors, right, on scales of 1 kilometer cubed, as you all probably heard about this. Ice Cube, Nestor, Antares, Nemo, and so on. Ice Cube is, I don't know where that's coming from, whether it's from my cell phone, from this computer, but I'm just going to ignore it. It's probably from my cell phone. Ice Cube, for example, is this enormous detector under the ice in Antarctica, and their proposal of using the ocean as a neutrino detector, okay? So perhaps they've become aware of this because they read the physics archive or something like this, and they discovered that we have gotten funding for all these things, and people are constantly building larger and larger, it's probably my phone. Oh, it's in my bag, yeah, okay. So maybe you can turn it off. Yeah, thank you. So maybe this, for the first time, they're going to start contacting us this way. So what would be the beam choice? The beam choice is actually pretty obvious if you know any neutrino physics at all. Namely, that there are two kinds of electron neutrinos. There are, of course, three kinds of, there's electron neutrinos, muon neutrinos, and tau neutrinos. But only the electron neutrino is relevant here. But in fact, it's the electron antineutrino that it would hit an electron at some enormous energy. It would actually produce what is called glacial resonance. Of course, Glacial received the Nobel Prize for unification of electromagnetism and weak interaction. So as you know, the intermediate boson, W, usually we think of it as a very massive particle. It decays into a neutrino plus an electron. But if you reverse the process in quantum field theory, the anti-neutrino would hit an electron. At 6 point PeV, it would have an enormous resonance. And that's a sort of almost a freshman calculus calculation to calculate what the resonance energy is. It's the mass of the W squared divided by 2 times the mass of the electron. And since the mass of W is so high and the electron mass is so low, this is a huge amount of energy. So it's kind of fun to write a paper in which you talk about PeVs, which would put the LHC at some puny low energy physics. So a PeV is 10 to the 3 TeV. So at a sort of 6,000 TeVs, you would start seeing this resonance in a future accelerator. Now the range in water of a neutrino, that energy is about 100 kilometers. Now we usually, we're all brainwashed by the great poet John Updike, because John Updike wrote a famous poem about how the neutrinos passes through the lover's bed and through the entire Earth without being seen and so on, like ghosts. And we all know about how ghostly the neutrino is. But in fact, at very high energy, the cross-section is so large, as Pauli realized, that in water it can only travel about 100 kilometers on average. So the upward moving neutrinos are all stopped by Earth. So the signal for this would be if you have a very high energy neutrino moving only downward but not upward through the Earth. Now these planned detectors, the efficiency, et cetera, oh, by the way, I should mention that John Leonard, one of my collaborators, is a neutrino experimentalist. So he's responsible for the design of some of these detectors. So for once I actually know, well, I don't really know, but I could at least talk about the experimental component of this talk with some confidence since my collaborator knows about all this stuff. So the detectors would catch about 1% of the neutrinos. So it's entirely within our capability if somebody is beaming a neutrino beam at us. Okay, so now we talk a little bit about how we could imagine producing such a neutrino beam. And this is, in fact, almost within our technology. We just have to build an electron-positron collider. But it would have to be in a highly boosted frame. Now, as you all know, we are here within walking distance, or maybe in Northern California you don't walk. In Southern California, we're actually encouraged to walk. I heard that. So, as you know, there's an electron-positron collider near here. I don't know if it's still running or not. No longer using that, right? So this will be highly boosted at very high energy. So actually, it's a very interesting exercise in freshman physics. At this kind of energy, the electrons actually overtaking the positrons in a lab frame to produce a very fast forward moving beam of Z0. Now the Z0 would then decay into neutrinos and antineutrinos. So you can do a simple calculation about how focused the beam is. So for one problem with electromagnetic wave is, of course, except for a laser beam, it's very hard to focus. But a neutrino beam from 3,000 light years away, such a beam would cover about 3,000 astronomical units across. So if for each pulse you want the detector to catch about 100 neutrinos, you can easily do the calculation. You see that each pulse will contain 10 to the 26 neutrinos. So we, of course, do not know what advanced technology the ETI has for producing such beams, what the energy cost would be, etc. But that's their problem, right? Now, our problem is to build the detectors, not to produce the beams. So I think one of our depressing issues, then, if these ideas are correct, is to continually improve these neutrino detectors. And nobody needs me to tell them to build larger neutrino detectors. They are being built, and as we speak, they're upgrades to IceCube and so on and so forth. And I guess Adrian is particularly knowledgeable about this because when I went to Australia, I met some of the IceCube people. They're all from New Zealand and Australia. The proximity of those countries to the Antarctica is going to give them a huge advantage in the future. So a very rough estimate of the information rate. Suppose you use the time interval between pulses as the message, then what is the natural unit? Well, question mark, right? What would be universal? In the universe, the muon lifetime, for example, is 2.2 microsecond. And a minimum time that's now detectable, according to my collaborator John Leonard, is now 1 nanosecond, and eventually be 100 picosecond. So with this kind of number, you can estimate you can get something like 140,000 bits per year, which is quite respectable using this idea. Now, another beam design would be just a proton accelerator, a regular proton hitting a target producing a pion beam at 30 PeV, which is then switchable between pi plus and pi minus. That's very easy to do because by a magnet, you can either pick out the pi plus and pi minus. Of course, they bend in different directions. And in one case, they decay into muons, and they decay in a muon neutrino, and the other case into an anti-muon neutrino. So with such an accelerator, you can actually switch back and forth between neutrinos and anti-neutrinos, and you insert a shield to kill the muons, absorb all the muons. So on the other hand, people also thought about how to use neutrino oscillation to encode for information, and my other collaborator, Bhagwasa, is an expert on this. And unfortunately, after a distance of a few light years, it would all oscillate to a universal ratio of the three types of neutrinos, 477. So there's no way to encode with oscillation. But there are two ways of encoding with this setup, is that you can encode by switching back and forth between neutrino and anti-neutrino. So, and in addition, you can use timing because, and so by the way, I forgot to mention that because the glacial resonance only occurs with anti-neutrino, it doesn't occur with neutrinos. So you can see that whether the glacial resonance happens or not happens, and you can use timing. So you could use some kind of Morse code. Now you can now estimate what the maximum neutrino angle would be, and so on and so forth, again, by sort of freshman physics these days. And it turns out to be much, much narrower than the Z0 beam by factor 10 to the 7 in area. So from 3,000 light years away, the beam size when it gets to Earth would only be 0.01 astronomical units. So this scheme is probably much better than the previous scheme. So it's probably much better if the ETs reason the same way we do. They would build proton accelerators and not electron, E plus E electron accelerators. And of course, a civilization that can do this would be able to extrapolate the Earth's orbit over at least a few millennium. So they could Now, since our paper came out, so now time for an amusing interlude. Since our paper came out, first of all, neutrino communication has been demonstrated between Illinois and Minnesota. So the reason between Illinois and Minnesota is, of course, the National Accelerator Lab is in Illinois, and Minnesota is, of course, the Sudan detector is in a mine in Minnesota. Now, after that, of course, we were interviewed by the financial press. And so, as you can see, this is actually in Forbes magazine, which is a highly reputable financial magazine that, in fact, my wife subscribes to. And as you can see, the headline there is that neutrinos to give high-frequency traders the millisecond edge. So, if you, this is really going to get off the ground because once billions of dollars are involved, people are no longer joking around. So, if you can read the words here, it says, 80-some years after Wolfgang Pauli first postulated its existence, the lowly neutrino is now on the cusp of being harnessed. I like the word harnessed. Put a harness on a neutrino. To facilitate automated high-frequency trading through Earth itself. So what they're talking about is a lot of it is New York and Shanghai, according to the reporters I talked to. So, but my question for these guys is also, why lowly neutrinos? Why call the neutrinos lowly in the financial press? So my reaction to these guys is that Goldman Sachs should now fund neutrino research. But it turns out that in 1921, Henry Goldman, in fact, look it up on Wikipedia. His name was, in fact, Henry Goldman. I didn't even know that there was this guy. He did give a few $100s for the Stern-Gerlach experiment. And the Stern-Gerlach experiment, as many of you know, is the key experiment in 1921 that ushered in quantum mechanics. Okay, so in fact, there's this article in Physics Today, Stern and Gerlach, how a bad cigar helped reorient atomic physics. Now, today I'm not going to talk about bad cigars, so I'm going to skip over that part and jump to the role that was played by Goldman. So here it says that Einstein, there's a great deal of interest in Einstein and so on and so forth. So they apparently had a big problem with the Stern-Gerlach experiment. They had to raise money to support the Stern-Gerlach experiment. And so Max Born, whom many of you know, is one of the fathers of quantum mechanics. He took advantage of the general public's interest in Einstein relativity theory by presenting a series of public lectures in the largest lecture room available and then charging an entrance fee. And that was how he was going to finance so Adrian could take a hint from this guy. But after World War I, right, the money earned helped us for some months, but as inflation got worse, new sources of money had to be found. Remember, this is after World War I in Germany. So Born then mentioned the situation, quote unquote, jokingly to a friend who was going to New York, but he was incredulous when later he was told, a postcard arrived to say that he should write to Henry Goldman. At first I took it for another joke. So, but in fact, he did write to Henry Goldman, and a check arrived from Goldman. So Goldman, in case you don't know, is a founder of the investment firm Goldman Sachs and progenitor of the Woolworth stores. And it is not entirely impossible that Goldman Sachs could fund neutrino searches for extraterrestrials. Sorry? They should have taken out a patent. I mean, if it were a modern day guy, right? Actually, it's very interesting. So now this leads me to a second part of my talk. So my friends and I would talk a lot about how to use neutrino beams to communicate. And then finally, we said, is there some other way of using neutrino beams to communicate with another civilization? And this would be the line of thought. How would you signal someone, say on the other side of a noisy dinner table when everybody's talking? Well, one way is, of course, winking or blinking. Okay, that seems pretty obvious in hindsight. So, but if you want to transmit information, you have to encode. So one way is, of course, you can change the rate of winking at the other person. I got that, thank you. Or the phase, but I couldn't figure out what message you were giving me. I mean, so this lead us to our second paper, a message from the Cepheids. So I think many people in the audience, but not everybody knows this, so I might mention this, that it was a lady astronomer, and I guess they don't call them astronomers in those days, at Harvard College Observatory. In fact, if you look up the historical record, you know what they were called? They were actually called computers. Yeah, they're literally called computers. That was their job description. And their job was to sort through all the astronomical data of the time. So Henrietta Leavitt, Miss Leavitt, I guess she never married. I guess she devoted her life to astronomy. She discovered the luminosity period relation, which made cosmology possible. There's a very nice book, a recent biography called Miss Leavitt's Stars, which I recommend. So our paper, Leonid Kudryavtsky, Pagvasa, and myself, if you're interested, was published a couple of years ago. Now, what is a Cepheid variable? Cepheid variable is a member of a particular class of variable stars, and they're notable for very tight correlation between their period of variability and absolute luminosity. And they were actually discovered, perhaps surprisingly, in 1784. And it was named for some particular star. So Cepheid is not a name of a person, but the name of actually a star. This correlation was discovered by Miss Leavitt in 1908 and given precise mathematical form by her in 1912. And this relation is absolutely crucial for doing cosmology. It's what made cosmology possible, because it could be calibrated with great precision using the nearest Cepheid stars. So in fact, that was how we started cosmology, because with this distance method, we eventually found out that some of the stars that we see are actually outside our galaxy. And distances found with this method are among the most accurate available, and so on. Okay. So the idea is then to use neutrinos, because of their penetration and their speed, to deliver energy at controlled depth to stars as giant amplifier. So for example, several years ago, I taught an introductory course on the universe, and I recommend this book by Roger Friedman with the textbook we used was called Universe. There's a whole chapter on Cepheid variables. So Cepheid variables are actually on the edge of instability. They're bright pulsing stars with period of instability. It expands and then it collapses, and then it expands and collapses. And in fact, the interesting thing is that the dynamics behind Cepheid variables is actually very close to the dynamics behind a heart attack. So the heart is also a regularly pulsing system, and it also expands and then contracts and so on. So the idea is that if you use neutrinos, even if it's a relatively small amount of energy compared to energy being put out by the star, at some controlled depth, because neutrinos could penetrate, and you want to hit the star off center, and so it could function perhaps as a giant amplifier. And another argument that Cepheids would be used, because any civilization which can do cosmology, and of course the civilizations that cannot do cosmology, we might as well forget about them. That any civilization who know about cosmology would monitor the Cepheids as distance markers, as we do. So we monitor Cepheids all the time. In fact, Cepheids could be seen from other galaxies, from distant galaxies. For example, we see Cepheids in galaxies in the Virgo cluster. So there are 500 Cepheids in our galaxy. So they're not exactly rare, but they're not exactly everywhere either. So here's a picture from the textbook I mentioned about how the stars are arranged. And there's many astrophysicists in the audience, and I don't want to insult their intelligence by going through this list. But as you know, there are white dwarfs and giant stars and so on. And then there's an instability strip. And the classical Cepheids are on this strip, and then there's something called the W Virginis variable. And then there are all these Lyrae variables. And the Cepheids is usually a population of one giant yellow star pulsing regularly by expanding and contracting. I've already seen all this. And I already said all this. And there's different types of Cepheids, and the luminosity variation is due to a cycle of ionization of helium. So the key is that when the helium is ionized, the atmosphere of the star becomes more opaque to light, and so the light pushes the star out, it expands and then collapses again, and so on. So a typical light curve would look like this. It's sort of the brightness, I don't know what since I'm not a professional astrophysicist, it's some sort of brightness, some plot of brightness would go periodically like this, go down and suddenly rise, go up and suddenly rise, some variable. And it's a typical sawtooth pattern. And the sample data from the Hubble Key projects measured 800 Cepheids, from which people have deduced this period luminosity relation. Okay, so how are we going to tickle a Cepheid, or how do we imagine an advanced civilization would tickle a Cepheid? So at this stage, a rather preliminary stage of investigation, we want to avoid details here and just consider the big picture. So we guess at the energy input, how much energy would it take in order to sort of affect the star? So it's, probably some fraction. We're not going to be some 0.01%. It's 100% is clearly out of the question. It's some fraction of 1. And how fast do we need to put this into the star to have the effect? So the deposition time would be roughly saying the characteristic time of this star, which would be the speed, how long it takes sound to cross, vibration to cross the nucleus, the core of the star. And that turned out to be about 0.1 second. So, and we take the power to be maybe 10% of the stellar core output. So the power, by some rough back of the envelope calculation, the power may be 10 to the minus 6 of the luminosity of the Cepheid. So for a few days Cepheid, we would need a huge amount of energy, like 10 to the 28 joules or something. Perhaps it's significantly less, we don't know, because as I already mentioned, the idea would be to deliver the neutrino shock asymmetrically, off-center. And I guess if you want to induce heart attack in someone, you would hit the heart not right center on. But what we are counting on is solar technology. So we, of course, have made a start on solar technology, is that the ETs would have advanced solar technology and they could capture energy from the Cepheid itself. This seems to me a rather attractive notion and seems like a real possibility. However, I emphasize that we are just doing back of the envelope calculation here. And I understand from Adrian that there are a lot of retired engineers and technical people here. So if anybody wants to get into this subject, they're more than welcome. I'll be delighted. And it could be much less needed. There's almost no study on this, and it's perhaps not all that even that useful to get the detailed numbers. So let's imagine, where do we have to put the accelerator? So you put the accelerator on some planet around the star. You don't want it to be too close to the star. You don't want it to melt, right? But you don't want it to be too far in order to capture enough radiation. So it turns out accelerators are extremely efficient, as my collaborator explained to me. And I learned some technical term. It's actually from wall plug power into the beam power. It's only tens of percent of the wall plug power is converted into beam. So it's actually very efficient machines. Accelerators are based on well-known physics at lower powers and low energy, so but we need a large technology extrapolation. But maybe from the LHC to the kind of energy I'm talking about is not completely nuts. So one neutrinos of order about 1 TeV to deposit energy deep inside a star with exponentially increasing density. So here is another trade-off, right? You want neutrinos of very high energy in order to have very high cross-section, but of course it's more expensive to produce a high-energy neutrino beam. So there's some trade-off somewhere. There's some optimum energy. So we're no longer talking about PeVs in the first part of the talk. The first part of the talk was sending a direct neutrino beam to communicate with us. Now this is an indirect method. As I said, I'm less and less far out. So in the end, I'm almost, well, okay, not that far out. So of course, we need further studies to determine how little or how much energy we need to jumpstart the expansion. But we don't have to solve that problem for the present purpose, right? Again, we simply say that it's solvable and that the ETI would do that. So again, if there are any people here that want to get into the subject, I would be extremely delighted if people want to think about some of these details. Now, there's also no reason for ETIs to restrict itself to a single neutrino beam. If you're going to collect solar energy from the star, you might as well build a couple of accelerators. And in fact, they could play the Cepheid star, they play the star like a drum set in a rock band. It's kind of a reversal. It's not the rock star is actually being hit rather than the other way around. We did a little bit of simulation, but this is just to give us a rough idea of what might be going on. So we imagine that by sending a neutrino beam, we can shift the phases of the Cepheid oscillation. So this is just a simulation. So the ordinate is the stellar magnitude. The axis, the x-coordinate is the time in days. And the solid curve is some idealized Cepheid with a 2-day period and 2 magnitude luminosity excursion. So it has this sawtooth shape that I showed you earlier in the curve. And, and we imagine that the phases can be shifted with a neutrino beam. You can trigger phase shifts and advance or delays of 0.1 day. The units are arbitrary, and the sharpness of the transition does not matter here, but we really want to see what would the frequency spectrum look like. So if you, this is totally simplistic, I just mentioned, this is completely simplistic, but it's just illustrative. So if the Cepheid variable is not modulated in any way, then of course the frequency spectrum would just be a very sharp peak. But one that is being modulated, of course, there would be a lot of frequency and sidebands and so on. But the trouble is, of course, more complicated structure of this modulated case is not so obviously different from a noisy spectrum. So you could not immediately discern whether this is caused by natural causes or whether it's significant. That's the real problem. So in fact, then we had to look at the theory of Cepheid variable a little bit. And so for single mode pulsation, always find the theory is well understood. The simulation models produce what we see. Jeff Scargo was a student at Caltech, and he told me yesterday that the theory was well worked out by Bob Christie, and whom I have heard of, but whom I do not personally know. But there's a recent paper by, I'm not sure if I pronounced the names correctly, Smolik and Moskalik. If you're in the audience, I apologize again. I don't know if you. And they said in 2009 that for all higher mode pulsation, they have no clue where the higher mode pulsations come from. So precisely the kind of thing we're talking about. And so they say besides the simple claim that convection is necessary, and so on and so forth, and its origin is non-resonant, etc., so our knowledge of the underlying physical processes remain obscure. And so when people don't understand something, they could always say there's turbulence, or it could be some other things. So that is going to be the hard part in this game when you analyze the data. So the outlook, I'm coming almost to the end of my conclusion. I borrowed some of these transparencies from my collaborators, so I have no idea what this represents, this picture. Maybe I hope to find something like this at the SETI Institute, but not, apparently not. So the outlook is that, the summary and outlook is that we feel, at least we throw this idea out for people's consideration, that unstable stellar systems such as Cepheids can serve as gigantic signal amplifiers that's visible across the universe. Across the universe means at least in the next galaxy, and certainly within our galaxy. So we assume that a sufficiently advanced civilization would be able to tickle stars, of course, question mark, and then an advanced civilization would find it worthwhile to tickle stars. So that's, of course, many question marks, whether they even want to do that. Now, I think in our civilization it's clear that if so many years from now we have the technological capability of tickling a star, we probably want to do it, given human nature. So, but we cannot extrapolate from human nature to ETs, about which we know nothing about. Now, signatures of ET communication may be available in data already recorded, and that's the exciting part. Because data on the Cepheid have existed, actually, it turns out when we looked into this, has existed for like a century or more. There are archives of Cepheid variable data, of course, of different variable quality. And that a search of Cepheid, and perhaps when I say Cepheid, of course, I also include the Lyraes, other variable stars. So it would be worthwhile to look at the records, in my opinion, and it may reveal a way to enter into this galactic internet that everybody's communicating, except that we don't have a password or something. So it's 1, 2, 3, 4. So certainly a long shot, right? We don't know, but should it be correct, of course, it would be a huge thing. So there are many possibilities for ET communication. So certainly electromagnetic wave, searches for electromagnetic wave has gone on for several decades. And so what we are saying is merely that we should try all practical ones. And of course, once the neutrino detectors are built, I mean, if we get a signal, the signal will be there, whether you like it or not, okay? So, and then the beauty of the Cepheid suggestions, of course, that the data already exists. And we perhaps only have to look at it in an entirely new way. Maybe the way we've been analyzing it is not quite right. Okay, so I conclude at this point. And I have been in theoretical physics for several decades myself. And I have never written 3 papers that have gotten so much publicity as these. So if I am inclined towards publicity, it seems that SETI is a good area to work in. Financial press, all kinds of things. So I'd like to show you what else we have gotten. So The Economist, which is certainly an extremely serious and first-rate journal, they ran an article on our Cepheid variables. So in fact, they called it a modest proposal for an interstellar communication network. So this I didn't even know. It says that almost as soon as radios were invented, people speculated about using them to listen to extraterrestrial civilization. And since the 1960s, attempts have been made by sifting through signals in search of alien chit-chat. So that's using, and more recently using electromagnetic wave building antennas and so on. And more recently the use of lasers in telecommunication. But techniques that work well on Earth are not necessarily ideal for talking across across space. And for several years, John Leonard of the University of Hawaii and Anthony Zee of the University of California, Santa Barbara, have been proposing a different method, and so on and so forth. Now, a German friend of mine who saw this article, his reaction was that you have to give it to the Brits. Of course, The Economist is a British journal. That somehow they managed to work cricket into almost any discussion. So their idea of interstellar communication is to hit a cricket ball to Earth. Let's see. Okay, so finally, as I said, my work has become less and less far out since my original paper with Steve Xu. And although we still strongly advocate and believe in what we said in our paper, so that has also been written up in several places, and in fact it was written up in this book by Marcus Chow, whom some of you know, studied astrophysics at Caltech, but he quit astrophysics and went into writing popular books. So he wrote this book called Dispatches from the Front Line of Science. And I told him he really missed, I would, if he had asked me, I would have chosen the title, The Never-Ending Days of Being Eternally Dead, not just being dead. So he devotes in this book, there's a whole chapter on this idea that Steve and I had that started this whole game. So thank you very much.
Tony, if I could ask the first question. Can you elucidate for us the connection between the power beam going deep inside the star a little bit more, and how that will be able to affect the atmosphere of the star in your envisioned model of what would happen with that?
So I think a serious astrophysicist like yourself maybe should do a serious calculation. But my own understanding of stellar astrophysics, mostly from my graduate student days, reading Clayton, which I'm told is now out of date, that the star is surrounded by an atmosphere, and the real action doesn't happen in the atmosphere, but more towards the core. So the pulsation has to do with some what is going on near the core. So you need something to get into the core. So there are people that talk about, for example, in John Wheeler's book, and in fact I was a student of John Wheeler at Princeton, he talked about, he has this picture of interstellar garbage trucks dumping their garbage into some star. Actually it was some black hole, but I think there are also people talking about dumping stuff into a star. But that just surface, presumably it just vaporizes and burn up on the surface of the star, so that's not going to do anything. So the idea here is that you really have to get into the core of the star. And so neutrino is the only way I know of how to affect things. Maybe you have to tune the neutrino energy to affect the helium ionization, that I don't know.
Hi. So given that pulsars were famously initially hypothesized to be alien beacons until they figured out it was natural, say you go back through the data and you find a bunch of kind of fishy looking noisy data that might or might not be alien civilization. How do you separate potential alien signals from a physical process of turbulence that you don't yet understand?
Well, exactly. That's what we said. You know, if you read our paper, that's what we said. Obviously that's the right point. Yeah. I mean, at LHC you have 5 zillion data points, and how do you separate out the signal from the noise, right? That's exactly. Yeah. Now the difference in pulsar, of course, the period was extremely regular. Sure. Yeah. So we're talking about, if in the pulsars story, when Taylor saw the pulsation, suppose the pulsation were changing from, it become faster or slower, faster or slower, then there would be something really interesting going on, right? But as we know, it's actually going slower and slower because of general relativistic effects.
Yeah. Would the planet that contains the advanced civilization that's sending out the signaling neutrino beam, would that have to be in the proximity of the Cepheid variable? In other words, do Cepheid variables actually have a habitable zone where it's likely that one could find such a planet, or can that planet be, say, much further away in a more hospitable, around a more hospitable star?
Yeah, I of course, nobody knows the answers to these questions. But that's of course it is an interesting question. But my personal just a guess, just a wild guess, is that a civilization able to take over a star presumably going to be able to travel the interstellar distances. So there's no reason why their home planet would be around that particular Cepheid variable. Could very well be around some other star.
I'm a bit confused. So the energy required for your tickling a star idea, you put that into a conventional radio beacon. It's detectable at 100 times the distance with a 10-meter telescope. Why would anybody want to do this?
I'm sorry.
It seems incredibly energy inefficient.
It's the second part of the talk about tickling the Cepheid variable. It's actually a relatively low energy beam, right? It's we were talking about TeV beam.
Not the energy of the neutrino, the total power used to produce the beam.
But the power, we're going to get it from the Cepheid itself by using some sort of solar technology. I'm not sure what you have.
And it's detectable over the entire visible universe.
So you want to transmit by electromagnetic wave again, right?
Well,
You
transmitting by EM, it's just
yeah.
the entire star.
Yeah, fine.
We'll talk more about this later.
No, okay, we'll talk about this later.
I've got a question about, I'm over here.
Yeah.
The question about helium ionization. This concept is dependent upon the, I'm over here, by the way.
Oh, okay. Oh, okay.
The ionization potential of helium.
Yeah.
And I'm wondering if there's an additional play here by recognizing, I think, I'm not sure, that helium-3 and helium-4 have different ionization, slightly different different ionization potentials.
Mm-hmm.
Is that an additional play or additional modulation possibility by taking advantage of that small difference?
Well, if you have a good idea, publish. We haven't thought about it, and in fact, we pretty much avoided thinking about such details at this point. I should also mention that I have another collaboration going on with Jeff Scargo here, and some other people on a different grant, but we also have not gotten into such details.
If you ever get funding, let me know.
We have funding.
Tony, of course, we read your paper with great interest when it came out, and we spent, I guess now 3 years ago, we had an REU student that began to collect the data.
Yeah, I understand you did this with Jeff Scargo, right?
Pardon me?
Did you did this with Jeff Scargo?
Yeah, Jeff was an advisor on that,
Yeah.
and he's continued the work with another colleague.
Right.
I was interested to think about the fact that, and Michael, I think the answer to your question, this thing's omnidirectional, right? The radio, and okay, all right. When you talked originally about the galactic neutrino communication, one of the things that you mentioned was that it also allowed the transmitter to remain hidden and not give away.
That was the first part of the talk, right?
Right. But the Cepheids could do the same, could have the same benefit.
How do you hide the Cepheids? I
No,
thought it's more like a
the
beacon.
Cepheid, you know where the Cepheid is, but you
Right.
don't know necessarily where the transmitting technology is
Oh,
located.
yeah. No, that's certainly true. Right. So this is the question that the gentleman over there raised, that the home planet may or may not be around the Cepheid. It could be somewhere else. Right. Yeah, exactly.
So maybe this is more a question of interstellar
Yeah.
networking technology. But so with an omnidirectional situation like this, how could it perhaps play a role in a bootstrap operation to redirect recipients to more energy efficient channels? Perhaps two kinds of bootstrap. One, just a redirection. The other bootstrap is where you transmit information about the physical world and let the recipient use new physics for them to make a better connection.
I'm not sure I understand your question totally, but so one answer might be, as you say, if you want to transmit a lot of information, you could leave it in the form of an artifact and then transmit the information on how to find the artifact. But to me, a very likely thing is just to say that, hey, we are here and we are advanced civilization or something like this by saying that we know what the gauge groups are. Okay, so I think that some of the early attempts at I understand that long time ago that we sent out with some space probe, some plaque showing showing some human body or something and so on. And in my mind, it seems like if I'm an ET, I mean, if some ET, in my mind, of course, we cannot guess the minds of the ET, but it seems to me that ET would care less about that kind of details, but more about, how much math you guys know, how much physics do you guys know, or something like this. Now, I'm doing research with Jeff Scargo and our bunch of friends, and I'm also with John Leonard and our bunch of friends. And sometimes, we argue about what the message should be. And again, people have different opinions and different ideas. And, this field is wide open. It's not quite like particle physics or string theory in which, yes is yes and no is no. But we generally think thinking about the media is now more important than thinking about the message. What medium would you want to use and what medium would be best? And message, for example, one of my collaborators constantly talk about prime numbers, and to me, this fixation on prime number may be very limited to our civilization. And in fact, even if you look at human civilizations, I asked these guys. We know that the ancient Greeks were interested in prime numbers, but is there any evidence that other ancient civilizations, like the Chinese or the Egyptians and the Indians and so on, were they interested in prime numbers? And there's no obvious evidence. And prime numbers might be, another civilization, you can easily imagine an ET in which discrete variables are not that important to them. Everything may be continuous. I mean, we happen to have 10 fingers. But, you can imagine ETs that's just sort of a blob of mist or something. And, anything is possible if you read enough science fiction, which I don't. Which I don't. So.
All right. So I encourage you, if you have further questions, come up and chat with Tony. Tony, we have a special mug to replace that one that you've got in your hand
great.
there.
Great, thank you.
This is actually two members of an advanced civilization
great.
communicating amongst the stars,
Very good.
perhaps using Cephid techniques. So please join me in thanking Tony for his great talk.
Thank you. Great. Great mug.